Hello everyone, and welcome to another reality check. Today we're going to be talking a little bit more about drag and also a little bit about lift as it pertains to immersed bodies. We are going to talk about applications where effects of drag and lift are important, and also what tools we can use to analyze drag in real-world design of road vehicles. We will also be talking to the Queen's Formula SAE design team about how they manipulate lift and drag in the design of track racing cars. Recall the drag equation. Drag force is equal to 1/2 multiplied by density of the fluid, velocity squared, drag coefficient, and frontal area. Regarding changes to the geometry of the body, frontal area and drag coefficients are the two variables that you have to work with. Frontal area is straightforward, reduce the area and reduce the drag force. But drag coefficient is a little bit more complex. It is composed of two components, skin friction and pressure drag, also called form drag. Skin friction is a force resulting from shear stress applied from the fluid to the surface of the body as it flows by the body. It results from the viscosity of the fluid applying a viscous friction force to the body. Form drag, on the other hand, is a result of pressure fields forming around the body. Fluid slows as it approaches the body, and an increased pressure is applied to the front of the body. Similarly, the low pressure zones will appear at the back of the body. Lift follows a similar principle. Pressure differences between the top and bottom of the body resulting from its geometry will generate a lift force. This is the governing principle behind most airfoil designs. So you may be asking yourself, that's great and all, but where do drag and lift forces matter? Well, the short answer is anywhere where there is fluid flow over a body. Planes, helicopters, turbines and compressors, boats, road vehicles, I could go on, but in this video specifically, we're going to learn a bit more about how drag and lift pertain to the design of cars. Wherever possible, it is important to minimize drag force on production cars. The higher the drag, the greater force the vehicle must overcome in order to increase or maintain its current velocity. Limiting drag is very, very important for maximizing the vehicle fuel efficiency. Lift is important to car design as well. A car's tires maintain traction with the ground due to static frictional force, which is directly proportional to the force that the car's weight applies to the ground. If a car experiences too much lift, then the car will have reduced traction. In other words, the maximum sustainable turning speed will decrease. Some sports cars will actually implement geometry, such as spoilers, to produce a negative lift coefficient. Negative lift, referred to as downforce, allows a car to maintain traction through high-speed turns. Flow over bluff bodies, such as road vehicles, is a complex concept in mathematics. Due to effects of turbulence on a flow and also relatively complex geometry of vehicles, it is not currently possible to determine a mathematically closed-form calculation of a car's drag coefficient. There are typically two practical solutions for calculating drag coefficient. 1. Experimental measurement of drag as a function of velocity using either a wind tunnel or scaled model in a water tank. Wind tunnels, in particular, will give accurate performance results, but they require the car to actually be built before any testing can take place. The second option, computational fluid dynamics, or CFD. This is a numerical approach to the problem which uses computer software to simulate flow over the body in order to calculate lift and drag forces. Its advantage is that it can be performed before the car is manufactured, but the model will never be 100% accurate. In addition, CFD models are only as good as the user. It takes considerable expertise to be able to correctly model a system as complex as a moving vehicle. In order to learn a little more about designing the aerodynamics of a car, we are going to talk to some members of the Queen's Formula SAE design team. So I'm here with a couple team members of the Queen's Formula SAE team. That would be Matt and Clinton here. And we're going to talk a little bit more about what they do on the team. So Clinton, could you tell us a little bit more about what your team does?
All right, so we design and build a Formula-style race car every year from the ground up. So we design the frame, suspension, powertrain components, as well as aerodynamic components. We test and then validate them, and then we go and race the car in 2 competitions.
So with each iteration of your team's design, what are some fundamental goals you have with regards to the lift and drag and aerodynamics of your car?
So we look to maximize downforce as much as possible to make the forces on the tires larger. This allows us to go through corners a lot faster as we grip the road. So we try and maximize that downforce while reducing the drag, because obviously the drag force on the car slows it.
So yeah, what's the trade-off between the downforce and the drag then?
So generally, as you increase the downforce or lift coefficient of the wings, you induce more drag.
Right.
So in this case, it's always trying to engineer that last little percentage to get the best lift over drag ratio.
Cool. Okay, so what features of the Formula Cars aero packaging help achieve the kind of goals that you're looking at?
I'm going to let Matt answer this question.
Oh, yeah.
Okay. So what we do when we design the Formula Car is we use as powerful a computer as we can find to break the air up into little tiny bits, and then the computer calculates the airflow using little tiny discrete pieces, and then it puts them all together, and you get a numerical approximation of the airflow. So you make some assumptions, and the computer gives you its best guess at how the air flows over the car. The reason this is beneficial rather than saying going into a wind tunnel is you can try many different designs without ever actually having to build anything. You can all do it completely virtually. So we generally, based off Clinton's laps simulations and our goals, we look to try and achieve a lift coefficient and a drag coefficient that would help our car get around the track that much faster.
Okay, and what kind of features of the aero package itself kind of help achieve those goals?
So in Formula SAE, we look to put as big a wing as possible on the car because we're going at fairly low speeds. So we basically, if you turn an airplane wing upside down, instead of lifting up, it's going to suck down. Some of the more interesting considerations, though, is because you have wings at the front, the airflow from the wings at the front actually affect the wings at the back. So you have to have some pretty funny-looking things on the front and rear wing, or on the front wing to make the rear wing actually work. So you see the front wing will turn up some of the air, and it'll actually be hitting the rear wing at a strange angle because of the aerodynamics at the front.
Right.
So it's really making it all mesh together, which the computer lets you see and do.
Okay, that's cool. So, and of course, compared to say an airplane or something like that, there are some considerations that are kind of unique to design the aerodynamics of the car. Do you mind mentioning a couple of those? What might there be?
So we work in the cars obviously traveling near the ground, so we have to deal with the ground effects. So the air accelerates between the floor of the car and the ground, and that's an important consideration. So we shape the ground of the car to maximize lift. And obviously, compared to an airplane, we're going for much higher lift coefficients, and we can tolerate much higher drag because the engine is able to overcome the drag forces. So an airplane, it's flying at a very low drag, whereas we're looking to get as much lift out of the car as possible. We can tolerate a slightly higher drag penalty.
And lift in the form of downforce.
Exactly. Sort
Okay.
of downforce, yeah, some negative lifts.
All right, yeah, thanks for talking with us, guys. I think that gives us a good idea of how you can work with aerodynamics. So hopefully after watching this video, you can appreciate the importance of drag and lift to automotive design. See you next time.